Now we're going to move on into the last of our clutter topics, birds and insects. This lecture is going to be divided up into 5 pieces. First, the general properties, the population, densities, migration, variations, cross-sections, velocity distribution, and the effects of birds on radar. You might think that this is a rather a topic, then why really are we talking about birds? And with radar, when we think of radars as viewing aircraft, which are relatively large targets, but there are a number of targets where birds are about the same sizes as aircraft some of the time. We don't know in the published media the size of low observable targets, and there are some objects, one of which I showed you in the radar cross-section lecture, that was of an artillery shell, and there, when we go through and look at the cross-sections, the sizes, they're about the same size. In addition to that, there are huge numbers of birds. When we think of our normal understanding of bird populations, we look up in the sky and we see how many birds do we see. Well, we're using our eyes, and it's a poor sensor to make a judgment about how many birds are out there and what would be their interaction with radars. And it fooled the people that first developed air defense radars after World War II, worrying about an attack from Russia over the poles, when they developed the first really important air defense system for the United States. When that was developed, birds were a big problem, and they had to identify them as a background and characterize them. And that was in the 50s, the late 50s, early 60s. A lot of work has been done in different kinds of radars, and you'll see. So it's a very important subject. And I'll point along the way as we look at these, I'm going to show you, because birds have so many different issues that come into play. It's a cursive dimensionality. Are they migrating, or is it localized travel? Is it land over ocean? They vary with geography, height, during the time of day, season, velocity distributions, and how they affect different waveforms with the ambiguity resolution, things like that. So birds are a very important topic. So if you get this far in the talk and you're saying, gee, the rest of this lecture is birds, forget about it, it's not true. Also, as a side issue, radar ornithologists for decades have used radars to understand migratory patterns of birds. And likewise, we radar specialists have learned an awful lot from the ornithologists about the migrating patterns of these targets, which we want to learn how to reject so that they are not mistaken for real targets. So let's just start in and go through the business here. We've got about 30 view graphs to go through. First, general properties. Okay, a good model for bird. And I was told this by Bob Richardson, who's long retired from MIT Lincoln Laboratory. I was told it back in the 70s. A good model for birds is a flask full of salt water. Their body is like my body and your body is a good conductor. The wings aren't great conductors, but the body is a very good conductor. And I see over here I have an Ehrenmeyer flask, and it's got some liquid in it, but just, it's that body that we worry about, that reflects. There's not much reflective material in the wings, although they're obviously very important to the birds. And the expanding and contracting of the body at the frequency of the wing beat is the dominant contributor to the individual bird's cross-section fluctuations. So from a physical sense, when one sees a bird in the cross-section going up and down, that's because of the wing beat pattern. And since many birds are often in the same range azimuth cell, the net total backscatter is the complex sum of each bird moving relative to each other in and out of phase and amplitude. Well, the amplitudes will fluctuate according to their own, but they're going to move out of range phase in and out. As this flock of birds would move think of like a school of fish, or when you've seen a large flock of terns by the ocean, if you happen to live near the ocean, come and land on a sandbar, and then a dog will go chase them and they'll all take off. But there's a relative velocity. They have one relative to the other, and those range differences all add up in a very complex fashion to give the total backscatter within the range azimuth cell of the bird. And here we see, these are photographs of a snow goose and a seagull. And I told you the Ehrenmeyer flask. And here are some general properties of birds that are just good to say in words right off, and some of them I may have said. Since birds move at relatively low velocities, if measured, that velocity can be used to preferentially threshold out the low velocity birds. And we can make a direct measurement of Doppler velocity if our signal processing system will allow us to do that, or to take at different times, and for an individual bird, we'll be able to see that it moves at a rate of change of range that's below 50 miles an hour, and that can be thrown out. The velocity from successive measurements of spatial resolution and range and angle is how we do that. But even though the bird echo is relatively small, they can overload a radar with false targets for two reasons. Bird densities are often huge, and I'm going to point to the numerical examples. And bird cross-sections quite often, or fluctuate to large values, and the sum total of the cross-section of the birds that are in a range azimuth Doppler cell, they can fluctuate to large values in amplitude. And as I said before, a huge amount of relevant research has been done over the last 20 years. The populations of bird species and their migration routes and patterns and densities have used the U.S. weather radars. Before the universities would have their all smaller radars, but we have an excellent distribution of weather radars, the NextRad radar, and they're located all over the country, overlapping pretty much. And that data, which comes out in range azimuth Doppler bins, is excellent at quantifying the radar observables so that you make good models. And major university laboratories have been working hard on this effort, using it for radar ornithology. And two major institutions, Clemson University and Cornell University, are world known for their experts in radar ornithology. Okay, now let's move on to bird populations and densities. First, let's look at migration. These are some view graphs that were taken from the web. We re-rendered some view graphs from some other sources, and you can see that the northern flicker, for example, breeds up here in Canada. It's year-round over the whole United States, and it winters down in this area of Texas and of California. And the Virginia rail, it breeds in this northern section of the United States, but it will winter down in Mexico and the very southern parts of the United States and Florida, and in between it will be year-round. And likewise with the gadwall. So and you know there are thousands of different birds, and this is these are to put in some little catching things that when I read them I said, wow. Along the Gulf Coast during the breeding season, wading and seabird colonies exist that have many tens of thousands of birds within the colony. 10,000 birds are quite common. And these birds are large, they weigh up to 2 pounds, and have wing spreads of 1 to 6 feet. So just imagine 2 pounds of salt water flying around in tens of thousands. So, and that's just in the Gulf Coast. And here's another set with the spotted towhee, the black tern, and the northern harrier. And this shows their wintering year-round, summer non-breeding, and breeding areas, which go all over. The black tern up in northern United States and southern Canada, but that migrates down and winters in South America shores and the shores along the southern part of Central America. And you can see there's a huge amount of migration. In the lower Mississippi Valley, over 60 blackbird roosts have been identified with greater than 1 million birds each. And many smaller roosts exist. And these birds disperse several tens of miles for feeding each day. So there's a huge amount of motion of these birds at higher altitudes, and we'll get into the altitude population densities later, and at the lower altitudes, where they be in the lower near portions of the beams. This is just to give you a feeling that they're all over the place, even though you can't see them. Now, for density of North American birds, some data was taken in the 50s, and this was taken in the New England area in the evening of the 3rd to the 4th of October of 52. And they had 286 sites. There were 1,200 observations, about 3,000 count hours. And you can see that in terms of the density, and this is a log scale down here, I mean, 10% of the time we were getting, probably 250 birds per square mile. Half the time migrating with about 25 birds per square mile. And if you think of a radar that's, say, 100 miles by 100 miles for a longer range radar, that's 10,000 times these numbers. So it's an area effect that can greatly, particularly during a migrating season, it gets overwhelming. And here's some migratory patterns that were noted by tracking radars. There was one on a Texas tower. That's an oil platform where there was an offshore radar that was used in air defense back in the 60s, and one at Truro. And they spotted coming down from along the coast and out from the northeast, huge bird migrations. Now, these bird migrations were tracked very effectively by university ornithologists. These are birds that go up to 17,000 feet, relatively small birds. And there was an article in Scientific American about this. And they go up to 17,000 feet, were tracked by radars on Bermuda, still at 17,000 feet, and they only came down when they went to Cuba or the northern South America. And this is hundreds upon hundreds of miles out into the sea. Just an amazing feat. And I'm sure many of those birds, they develop as much, something like a polar bear, feeds, and the bears feed with lots of salmon or food or seals or whatever, and then they just live off the winter on it. These birds would go at, going with the wind, helping them, at probably 30 miles an hour, net relative to the ground for down the whole coast without landing. Although some birds from Canada will land in the winter along the coast as it gets warmer to replenish their food and their energy stocks in their body. But this set of birds go all the way down. It's nonstop, Boston to Havana or to Aruba, that kind of a flight. And a great many of them don't make it, but certainly this has been going on for hundreds of years. Plenty make the entire trek in swarms. And these are the bird migration patterns across the Mediterranean Sea. You could be in the middle of the Mediterranean in the fall or the spring, and there's enormous migration across the Mediterranean. So if you built a radar to say work on an island out here that's 100 miles away from land, when you add up the 2.5 months of the spring and the autumn migration where there's heavy migration, there's a heavy bird population. This was all documented by, I don't know if it was rather just an interesting fellow, by a fellow on a British aircraft carrier. His name was Casement, as I believe. And it's talked about, his paper is talked about in Eastwood, reference 8. There's a book called Radar Ornithology. It's out of print. I know the Lincoln Laboratory has one copy, and but I've got from my history of all of working in over many years in this type of work, I've got his original papers, and I got them from a Natural Museum in Philadelphia when I was working there in the 80s. They had them in their archives. Now, when you look at the altitude distribution of most birds, it tends to be about 3,000 feet. And these, again, are from Eastwood, and it's nightly migrating birds in England in 1966. They go up to 7,000 feet, but these are averaging about 3,000 feet, some. And the distributions obviously differ from migrating and non-migrating birds. The presence of cloud cover affects the height of the distribution, and the distance of the migration can influence the migration altitude. As I said earlier, these are at 3,000 feet, and the ones from U.S. to South America, that's the northeastern part of U.S. to South America, are up at 17,000 feet. And now, to show you some here, some time-compressed radar data of bird flocks. This is one of the more interesting ones. All these little dots you see, for the most part, are birds that are leaving their roosts in the morning to go feeding. This data was taken Wisconsin. This data was taken near Green Bay, Wisconsin, and ring roosts are flocks of birds leaving their roosting location for their daily foraging to go get food just before sunrise. And at sunset, the rings will come back and they'll compress down. And the location of this particular roost is on Green Island in Wisconsin. This data was collected that you see here in a cyclic loop, was collected between 5:25 and 6:15 in the morning, and you see the 50 minutes displayed in 1.5 seconds. So it gives you the idea of the motion. And this data was taken with the S-band WSR 88, the next radar that NOAA has. NOAA has the order of 200 of these radars throughout the country, and they're used to evaluate storms, with what the weather's going to be, that sort of thing. And you probably see them when you watch your weather forecast, this data. In there, they have two displays which they mainly use. One where they display the size, the amplitude of the return, and it's measured in dBz, and I'll get into that in a minute. But there's another display they have which displays color-coded also the actual Doppler of the return. And you see this goes from the scale of 80 dBz to minus 30 dBz. That's 110 dB. And it's an interesting exercise, I'd say, for the student to look up on the web what the characteristics are of the WSR88 and just see how there's a little yellow patch when the ring is about there. When it's in this stage, when it's around 30, 35 dBz, calculate what size cross-section that is. Before we've gone over what the cross-section per unit volume of volumetric clutter is, and weather radar people use this quantity dBz. And in Merrill Skolnick's book and in weather radar books, they go back and forth. They explain how you derive dBz from the attributes that the weather radar or the radar can measure, a volumetric backscatter. And for that problem, you should say just how big in radar cross-section is that. This is Green Island.